So hello everyone, and today we'll be seeing one of the problem from Geeks for Geeks. It says count indices to balance even and odd sums. The problem can be explained in a better way, I think, because these numberings or this description is quite misleading. But anyways, let's get started. So we are given an array ARR. Count we and now the problem statement begins now. Count the number of indices such that deleting the element at the index and shifting all the elements after it one position on the left in an array where the sum of elements at even indices equal to sum at odd indices. So what does it mean? What does it mean basically? So if you are given an array like this, first of all, let's be clear on what they want. They want from us is a count. Count needs to be written, and that's true because we are returning an integer. That's correct. Now going forward, if you are provided an array A, which is this, then they are expecting us to return the count in such a way that if we are deleting one element from the array, the left index sum and the right index sum would be equal. So let's bring indices in the picture. So this is 0, 1, 2 and 3. Now they are expecting us to delete an element. Let's say we delete element at index 1 at 1. So what would happen? The array would look like 2, or instead of bracket I'll write it down 2, 6, 4. And once we have this, let's mark it. So the indices would somewhere look like this. And now even sum would be indices at 0 and odd would be indices at 1, which is 6. Even would be 2 plus 4, which is 6. Now 6 and 6 both are equal. We increase the count by 1, increase C and T plus by 1, and we return count. If we found any other, we do the same thing, and in the end we return the count. So obviously the count would not exceed the length of an array, and minimum it can be 0, because even after removing anything they are not equal. Same thing goes with example number 2. So no matter you remove this, this or this, sum of even and odd would be equal. So no matter in that. So that's correct. And with this understanding into picture, let's understand how can we solve this problem. There is one approach which directly comes into my mind is knife, which means that hey, we can just go ahead and remove this, remove an element, shift it and check it, and this will do for all element in array. So taking an element from array and shifting and checking the array, check the sum, I'll say, would cost us O of n square, because one is loop to iterate from the elements, another is loop to check for the sums. Okay, that's cool. What is wrong with this approach? Few things that we can do better. We can do better in the sense of, yeah, we have to have let's say better approach. So we have to have a loop for all elements, because that's what we are getting to understand, hey, we can I remove this element, that element, etc. So we wanted that loop, but recomputing the sum doesn't make sense. So can we reduce this complexity? complexity. Yes, and that comes out correct. We can reduce that complexity by pre-computing the numbers. So what I mean is, if I have an array like this 2164, I'll just quickly note it down, 2164, and we have index at 0, 1, 2, 3. So we can pre-compute the array in such a way that we have understanding of even sums and odd sums. So even, and there is odd sums. So since we are at 0, which is an even sum, we can tell it as 2. Then we come at index 2, we increment the sum from 2 to 4, but within index 1 we'll just keep it as it is, because no increment, no contribution from index 1, and we are currently carrying out the legacy from 0 and 2. 2 is valid index. What is element at 2? 6. So let's take this. 6 plus 2 is 8, and then we have 4, which is index 3, which is not contributing, so 8. Index 1, which is contributing, well and good, so I'll just mention it as array. And these are indexes. 1, which is contributing, so we add as 1, 2 not contributing, so carry out 1, 3 contributing, and we have 4 with current value is 1, which gives us 5. So cool. Till this point there is no big deal, but how can this two arrays, so remember this is an array and this is an array again. Okay, you might ask, hey, how can these two arrays help? So first of all, let's understand how can we quickly compute the sum. Quickly compute sum. So these are the small arrays, so the idea would not strike immediately, but it is very good to visualize how the problem would go ahead. If the array was huge in number, this approach would benefit us a lot. Now quickly compute the sum. I'll tell you that how can we quickly compute sum from 1 to index 3. So index 1 to 3 or 0 to 3. So for entire array, that means entire array, and this is odd index, odd sum for index. So how do we compute this? We just go ahead, take the odd index at value, the maximum value, which is 3 here, and we check it 5 minus any of the value which we are pending. So in this case there is nothing, so 5 is our answer. 5 minus 0, and that's our answer. Because there was nothing, so I'm not removing anything. So odd index sum for index 0 to I would say not 0 to, but 2 to 3. So this is a partial array, and this algorithm outperforms or shines in such cases where we have partial. So I'll take an odd sum from 3 minus odd sum from 2 minus 1. Remember, we want previous of 2, that is the reason. And here it doesn't matter, because here we have 1 and 1 both are the same for index 2 and index 1 both. So it is something like we are going ahead with odd of 3, which is 5 minus, and we have next element as 1, so 5 minus 1 is 4, and that's what we get. Odd sum from 2 to 3, which is 4, and since 6 is not contributing because it is an even index. Very similar, but only for even now. For 2 and 3 we get not odd but even, not odd but even. So even at 3 is nothing but 8. 8 minus 2 minus 1. So 2 minus 1 is nothing but 2. So 8 minus 2, we go ahead and compute it as 4. Sorry, 6, my bad. So we have only 6. So this concept is known as PrefixSum. The only idea to explain these three was to let you know or let you summarize with PrefixSum. And now if you understood what PrefixSum means, we can get started. We can get started with how PrefixSum could solve this our problem. So remember we had a question, how can we avoid summations? So we are iterating for element in array. Now let's understand what can we do here. We can have even sum and odd sum, and within even sum as well we have left hand side and right hand side. What is left and right hand side? So we are simulating in a way that element is being removed. So left hand side and right hand side corresponds to left hand side sum of that element. Of course the element is removed, so we are not even counting the element. So in our classic example, if 1 is removed, we are not even counting 1. We are counting sum from left hand side to 0 and from I plus 1 to the right hand side. And similar case goes for LHS and RHS of odd sums. So once we get even and odd sums, or I'll say LHS side of even, LHS side of even odd. Once we got that, we would just go ahead and a simple if statement would be suffice, where we check even LHS plus even RHS is equal to odd LHS and odd RHS. Cool. Since this approach would work, further we can check the dry run solution once we have implemented our understanding. So what we'll do is, first we have a count variable and this would be our result. We can have long, which would be odd sum new long a dot length. I'll call this array as a long even is equal to new long a dot length. I'll statically check the set the values of even and odd of 0th index only. It would be 0 and odd of 0 would be 0. Why is 0? Because 0 doesn't contribute in odd, as 0 is even, and since 0 is even, it will contribute in even sum array. Now the entire game is to understand what is contributing to what based on index. So I'm running till 8 of length, and let's continue the legacy first. So even of I is equal to even of I minus 1. Similarly, odd of I is equal to odd of I minus 1. Now I'm going ahead to check if I modulo 2 is 0 or not. So that means it is even or not, and now it is even. I'm contributing this to even plus equals a of I, else you know the drill very well, odd of I plus equals a of I. Cool. Once we are at this moment, we are sure that we have even and odd data collected. Now we wanted to just simulate this way that, hey, can I remove I or not? So can I remove ith index? Cool. So for that I'll check the LHS, or I'll say even LHS. Sorry, I'm using snake cases. Okay, works. Even LHS I'm using to compute the even side, left hand side sum. So you know how the drill, how to calculate sum. What I'll do is I'll take the sum from 0 to I minus 1th index. So it would be even of I minus 1. But wait a second, we have I as 0 as well. So that would be a negative index. So what I'll do is, if I is equal to 0, I'll take 0 else I minus 1. Same goes for odd LHS. I'll take OLHS, and this would be for odd. So cool, we have LHS sorted. Let's go for RHS. So similarly, even RHS. So if you got even or odd, the rest of the thing is simple. So I don't want I within our example, and my ultimate thing is stored on the right hand side. So I'll take even of a dot length minus 1, and this would give me a sum of entire array, right? But I want this only till I, and I is excluded. That's the reason I have used even of I. So you remember, if I wanted to include 2, I do 2 minus 1, but I just wanted to include I plus 1, and I don't want to include I. That's the reason I'm just going ahead with I only. If you want, you can visualize this I plus 1 minus 1, and it will give you I. So similarly, not only this, we have for odd as well, but here you'll get odd. Yeah, and ultimately I'll go ahead and check for even LHS plus even RHS should be equal to odd LHS plus odd RHS, and if that is the case, I'll increment the count, and I'm anyways returning the count. Let's compile this to check for any compiler errors, and I guess yes, there are few compiler errors because we have used long. Okay, cool. So yeah, I have updated this value from long to end only, and this seems to work well. Let's submit this solution. So yeah, this was a classic example of prefix array, and I think the description could have been better.